Eddie, Elida.
Hey, Yogesh. Hi, Mita.
Hey, good afternoon.
Hey, good afternoon. We'll see how many people show up today, but hopefully a few. So when you all get to OCP, I made something humorous for folks that attend. I printed a big sheet of what I just pasted, just as kind of a gag. I'm not pointing fingers for dumpster fires at anyone in particular. The dumpsters are everywhere. But anyway, I thought it'd be fun to have a laptop sticker or something.
Nice, Drew.
Yeah, so I've got to cut them, but I've got
Oh,
more.
jeez.
I like
You're
it.
all in. You're all in on that concept, huh?
Well, it's they have a big printer, so I can use, and somewhere around here I've got to go dig it up in my pile of junk. I have RFID stickers that are good for laptops, like they're good for metal back things, and so you can put we can put the website in. So tap your phone to the sticker, and it'll jump to the website.
Pretty
So.
cool.
I get the whole picture, but what's the pirate hat for?
Just because we're a motley crew.
Okay. Speak for yourself.
Okay, well you're a lot more polished than I am.
I'm
Dean.
Suave and the Boner, right?
Yeah.
I used to work in a lab back at IBM that there was a huge Jolly Roger flag flying in the lab. So yes, I know what you mean. It's fun to have that image, sort of a skunkworks image.
We had there was a project I worked on called Buccaneer at HP, and we had a lot of fun with it. So yeah. But anyway, that's just for grins, it's nothing serious. And I'm not trying to make any big statements. It's just supposed to be humorous. Because we're often the people that get called when things have gone horribly wrong. So, uh, that's our specialty, right? And that's actually one of our biggest challenges, I think, as a career, just as we're waiting for people to join, is how do you explain how much trouble you've saved people?
Oh, you can't. I used to work. I used to work for a guy also at IBM. He was very smart and a little too clever. And he told me once, sometimes so he was a higher level manager, and when issues were being debated hotly, he would let them get out of control and turn into a fire, and then he would step in and fix it. And I thought, wow, that's pretty Machiavellian.
I was told to do that in a previous life. I'm not going to say where, and I refuse. I'm like not going to light a fire under my own rear end. I'm sorry. If I can help it. If I can help it being the key word. So yeah, let's fix crap. I don't know. So
Prevention is the best medicine, right?
amen.
But it is true. People don't appreciate it because they don't know what you saved sometimes.
Well, and like some of the work in FM was, and like some of the bounded fault work has been a precursor to just huge improvements in memory reliability in DDR5. It is DDR5. So normally when you go to a new memory technology, like from DDR4 to DDR5, you expect some trouble initially because people are working out the kinks with the differences. But the transition to DDR5 has generally been phenomenal, as opposed to the 3 to 4 was rough because there were ECC problems and misaligned assumptions, and we've worked through those and solved a lot of the problems. And so we as a fault management community have made an impact to the world. I mean, this is a really big deal that memory is so much more reliable. And it's not the memory. I'm not looking at you, Evan. It's a combination of ECC assumptions and memory layouts, and but getting everyone to work together, we did something awesome. And but it's hard to take credit for it. It's like, yeah, we prevented all the forest fires that occurred from memory problems, and people are like, cool, memory's reliable. They just kind of take it for granted.
Yeah, people pay less attention when things are going well, but that's okay.
I just want a cut of the money, but no. But anyway, and I think you know, hats off to the memory suppliers and the CPU suppliers for making big fixes. You know, things are way better. Okay, well, so I was thinking I would go over a few more poison slides, and that may be it. You know, maybe I mean we can talk a little bit about what's next. But then I think are many of you coming to the global summit next week?
I'm signed up. Yeah.
Oh, you're on mute, Hank. If you're
You've been talking, but somehow you're muted. We can see your lips moving, but can't hear you.
I will be there.
you will?
Alright.
Awesome. And I'm always happy to see you, Mita. It'd be awesome to see you in person. Cool.
So I looked at folks who responded. I think majority is going to be there on Wednesday. Wednesday is when we have a block party from 5 to 8. We meet at the usual spot for those who know, facing the event center, the front stairs. I think almost next to the left of the entrance. That's where we typically gather. So, you know, whoever is there first, start saving some space. And,
Hey,
and then,
Yogesh, Yogesh, hey, I'm not going to be there, but I received a cancellation for next week API meeting. Is that why it's canceled?
yeah, because
Okay.
are going to be at the event, that's why it's cancelled.
Okay, thank you. Because the meeting is still in my calendar, so it's weird. I don't know if it's for everybody it's the same, but so I know it's canceled.
Yeah, I have the same issue. So
Same.
somehow the way I added it, whenever I get a deletion notice, I have to go in and manually delete it from my calendar.
Okay.
Yeah, the group IO thing that we use, I don't know how well that works with the Outlook or whatever you're using. So yeah, there's that thing.
So it's a feature.
So I'm doing something kind of risky. I because I don't want to get a lot of spam, but I just posted my cell phone. I'm not super private person. I'm pretty much out there. So you know, if you ping me, just tell me your name if you ping me from the blue while you're there, and I can help you figure out where we are. So
Yeah, I was also going to say, I'd send a picture, blast a picture with a big circle and arrow. This is where we are, kind of thing. So I'll do that. Typically, I also do that by the time we get to the second, third day. We kind of have a text group going, and we can set it to coordinate. Okay.
Yeah.
All right. Looking forward.
yeah, super eager.
I may grab some of the DTMF people, Redfish or PLDM, and who aren't members of this group, so we can recruit them.
Well, and for what it's worth, Hari, Microsoft's representative, just built a prototype RAS API Redfish server based on some input from Carlos and I. And so Carlos and I are describing the concept to him, and he's building a prototype for us to play with. And it's nowhere near ready for prime. It is rough, but we're gonna work through that a few times. Come to the RAS API team, get it approved by everybody. You know, we're not trying to ram. We're just trying to make progress. So we're gonna make a proposal, have something actually working that we can demo to the RAS API team, and then with Harry's help, once the RAS API team agrees, we'll get it formally approved in DMTF. So anyway, I love it. I can't getting more of those people pulled in, and I can try to grab Hari because he'll be there as well.
I've worked with him for 15 years.
Awesome. Okay, cool. But yeah, I mean, things are starting to really come together. It feels pretty good. And the other news is that Yogesh and I met with, I'm going to mess up his last name.
Sarthi from HPE.
Yeah, thank you. And I worked with him back on the Superdome 2 days when his team first started working on RAS. They were brave enough to build the first error analysis engine that I worked on. And so I proposed this feature in Superdome that Superdomes would gather their error data and diagnose themselves. And Mohan's team built that, and it's still in use by HP. And so it's a good team. They're in Bangalore, India. So this is a particularly unpleasant time for him, being, middle of the night Saturday. So he may find another person to stand in for him here, but they're interested in the RAS API and FMFM. So we're getting a little bit more momentum. And I was blunt with him. My goal in getting momentum here is that if we align on what we want and what we're asking for from our suppliers like Intel and AMD and ARM and Ampere and others, then it's way easier for us to get it because we're all asking for the same thing. So, that's the purpose of this poison paper, is to get people on the same page. And it's like a lot of the requirements we're driving, if we can get alignment, we can come up with some standard ways to do things that help everyone. Make it easy for our suppliers and us. And so Mohan buys off on that. And HP, the part of HP he works for is the scale up part. So if you remember last week, I shared a Superdome picture. That's the part he works in. And so, they really, really care about adding value with RAS. And so they'll probably take what we do and go further. And so that'll be kind of cool because they may push us to think about things that are further than we've thought already. So cool. With that, I was going to go over my slides, but Yogesh, was there any other stuff we need to cover?
No, I don't have anything else today.
Okay. Well, this is going to be, we're going to continue to just be informal, and, I'm just doing this to help ramp people up. So I did add a slide early in the deck, and I just wanted to show people that that basically, I just want to show this flow. You have a memory ECC error, it goes to the memory controller to some sort of interconnect, to a cache, to a core, and then we'll discuss the details later. But I wanted to mention this because some folks were unclear. There were some questions about, hey, is this the security thing? That is not hardware errors, and the answer is no. This is really a hardware error. So this is an example of a memory access in a CC NUMA system. And then my intent is to share this deck, and I can leave it as a resource for people to use. So I'll save it as soon as I'm done, and I've had all your input in our work in progress folder. Oh yeah, go ahead.
Just to nitpick on it, it's not a big deal. I know what you mean. But you're using the word system interconnect there, which could very well mean SOC fabric, NOC. That's kind of caught
It's
badly.
both.
Yeah.
I mean,
Okay.
I'll just say interconnect. How about that?
Yeah, whatever. Yeah, sure. I mean,
The reason is Poison works across like QPI, and it works across the mesh. So it's a status bit that is transported with packets.
okay, so it could be, okay.
It could be hyper transport. It could be, if you remember HP, and HP has this fabric, so they have, CPUs and memory that are standard. They have something that pretends to be a UPI chip that participates in the snooping. It's like a 6-socket system, except that 2 of the sockets aren't sockets, they're agents. And the agents speak a proprietary protocol on the ends here. So all these crisscross wires, this is a glue logic system. This is a proprietary protocol, and this proprietary protocol has to pass Poison, and it has to pass viral. So that's just a general thing, any interconnect. And so when I said system interconnect, I really meant all the interconnects between the memory controllers and the CPU cores.
Fine, because between the controller and cache, I was thinking, is it just the network on chip or what?
There's more.
It's more. It could be the other socket too.
Yeah, I mean, because there are NOCs on each of these, so there's a mesh on these chips, but then there's something completely different across these links.
Okay, that's good.
Okay, so so I'm gonna scroll down and go back to I/O. I think we talked about PCIe error containment and how software always loses the race. I mean, that's just the way, like that's a good way to think of error handling, is that, if something's gotten corrupted and you're counting on an interrupt service routine to do something about it, just assume software loses the race, because software by definition takes a little while to enter the ISR and to figure out what's going on and to save some context and branch to the handler and walk through some things and get to the point where it can react to the error. And in the meantime, hardware transactions are flying through the system, and they're not waiting for the ISR to run. So software loses the race. And so, if we're going to implement containment correctly, we need to make sure that we have transaction level responses where they are needed. And so poison is a classic transaction level response. And we mentioned, some PCI devices will fail operations when they get the corrupt data, and some don't. The consumer market in particular has plenty of devices that they don't have to worry about poison because none of the systems that they're intended for have ECC memory. So, why put a lot of effort into something they don't ever expect to get? But the problem is then someone decides to reuse those things in a data center context, and now we have a containment concern.
That's another thing that's always bothered me, right? I mean, there's typically, as an OEM, there's a qualification criteria. You cannot just plug in any card into your system. I mean, you can, but then there are no guarantees, right?
Yeah. But I think okay, and this is actually interesting. One of the reasons why I think this is poorly tested is that to test poison consumption, you would, like on a PCIe card, what you would have to do today is poison main memory in a place where the driver is using the data, and then do something in the driver to get the card to consume that data. And the process for doing that varies, vastly between PCIe cards. They're all extremely different. And so it's really hard to test that because there's no clear, it's, like Intel and AMD are really good. And a lot of ARM chips, they have tools for injecting memory errors. But mapping that to something that will get pushed out the PCIe link is somewhat tricky. And so a better shortcut for that I've been advocating for the last few years is, why can't we have something in the root port when we do our error injection that says, okay, the next MMIO transaction you see, poison it. And we could poison a class of transaction, and that way we can be sure the card got the poison without having to wonder, did we get the memory address right? Because it could be that nothing happens, right? You poison some memory, you think you DMA'd it to the PCI device, nothing happens, and now you've got to go like look on the far end of a network device or look at a file that was saved and say, can I find the flipped corruption? But it's really hard to correlate the memory address and the file name and blah blah blah, all across the path. So if we could poison TLPs directly, that would be groundbreakingly helpful in proving that PCIe cards do or do not support poison correctly.
But what you're proposing there, Drew, is by poisoning the next access, it's kind of a random poison, right?
Yeah, but it's
You-
an
you-
MMIO, and like you
Mhm.
say, like you don't want to do a config read or write. What I want to do is say, like I can get a PCI card to do DMA, no problem. Just lining up the address with
Mhm.
poison
Yeah.
injection is hard. So if I could just say, well, I'll just start using the card and start hammering poison into it periodically. And if I see no errors from the card and no failed operations, at that point, I'm super sure that I injected poison because I said, inject the poison on the next MMIO.
Mhm.
Did you see, does that make sense, Seb?
Yeah, I understand, but it's just because in the past I've seen like similar issues, but they're more for like testing, even DRAM, when some memory controllers do not allow you to inject on an address, but to inject on the next access, and it makes debugging and kind of understanding what's going on really tricky. But
Yeah,
yeah, I see where you're going.
I mean, if you did it, maybe if you were really clever, what you could do is inject on the next MMIO and then log the address. You know, the PCIe address of the MMIO that you poisoned, just in an injection register. Say, okay, I did it. I poisoned this address. Or you know, maybe we could inject errors in a certain PCIe address if we wanted to be clever. You could say, well, you know, match the PCIe address, and we could. If we knew how the IOTLBs work, we could, you know, just say, oh, well, we always map MMIO at the bottom of this card's address space. So if I inject somewhere in there, it's probably okay. But that's just really hard to do. It's really hard to align the poison injection with the operation that the card's doing. And here's the thing, the cards that we want to test the absolute most are the ones that migrated from the consumer market. And those are the ones that ironically are the ones that are going to have the least mature error injection capabilities in the card itself. Like the vendor will generally have the weakest support. So, you know, it's when we that's why we need help from people that design root ports. So hopefully that makes sense.
Yeah, I think there's a lot of work there, but I agree with you. It would be good to work with the root port PCIe community.
And like if you look at you know, poison handling today, you know, I can tell when I've been talking to many of you about this, but I can tell when a CPU consumes poison that something bad happened, and that generally that it consumed poison. But I can't tell where the poison came from at consumption time. And I understand that you need to know where the poison was generated. And that's you know, that's what I say here. The problem is that PCIe endpoints, if they have something like HBM or LPDDR or GDDR memory with ECC, they can generate poison. They can poison memory in the host by sending poison TLPs upstream. And there's no standard way for us to tell. Every vendor does something completely different. And some of the most important vendors, you know, aren't really focused on telling us that poison was created. The error logging isn't quite where we want it to be. And so one of the hopes of the RAS API, just as an editorial comment, is that if I have a PCI endpoint that supports the RAS API and it generates poison, I'm going to be like, hey, you generated poison. That is a serviceable event. Please, sorry, my phone's ringing up. It's not too loud. Please log an error that you generated poison so I know that you're the cause. And what I'd like to see, and this may be something we want to talk about and work on requirements for, but so when a RAS API endpoints generates poison in another address frame of reference other than the host SOC system addresses, then we kind of need to know that. So, you know, PCIe endpoint might poison an MMIO address, but there might be an IOTLB in here that remaps that address to another address in the host. And so if I have a RAS API endpoint that says, well, I sent a poison TLP on this, you know, PCIe address, then I need a way to correlate that. And so, you know, I think that's going to be a future topic for us, is to make it a little bit more traceable when things are having problems, so that as we build bigger and more complex systems, especially like for, you know, AI clusters, we can get a more accurate handle on where our problems are.
So I don't know if there are PCI experts here who are familiar with PCI version 6, but I do believe that the version 6 brings along the ability to inject specific errors and maybe even construct, have some power over constructing the TLPs. So possibly it's there. I'm not 100% sure. I did hear that it was.
Okay. Well, and like we had talked about it before, and so I've even looked at, I was talking to Ant Micro, a company, they're a European company, and I was working with them on a Rowhammer attack tool. ETH Zurich just published a paper. This is for attacking memory, and it's an open source FPGA-based DDR5 and DDR4 memory controller. But Ant Micro was saying, hey, we could help you with PCI injection if you want. And they were talking about putting an FPGA in the middle that watched the packets and mucked with them. And so you could do that over the link. You could have a repeater or something that messed with the packets. And then like some PCIe switches give you the ability to fabricate a packet, which is okay. Fabricating a packet's okay, but the problem is if you fabricate a packet, you're not 100% sure anyone's paying attention because you don't know if the packet you messed with was involved in an operation. Where if I can mess with transactions that are already in flight, those transactions were initiated by software trying to do something. And so you're more likely for software to notice that something they didn't happen if you mess with a traffic in flight. So that'd be awesome if they've said, hey, we'll formalize messing with traffic in flight. That'd be amazing. I'll go take a look and see if I can find it. But I do think there's work here. Like we don't really have a good handle today on poison generation in PCIe endpoints, and it's becoming a more and more common thing as cards get more and more memory, and we get more and more sophisticated PCIe devices. So another fun case, and I think I covered this slide, right? That it's pretty clear that we want downstream port containment if we use it to be on the furthest downstream link possible. So if I were to trigger DPC on link 2, I take out everything downstream of the switch. But if I trigger it on link 4, I just take out one endpoint, and that's better. So we generally want to make sure that we are able to configure it as far downstream as possible.
So Drew, that one, the downstream port containment case is only when you don't quite know what you're going to hook up to your PCIe port, and it may be some kind of older or device that doesn't manage poison, right?
Yeah. Well,
if you have poison, you never need DPC. Do you agree?
No. Well,
No.
okay. Let me put a nuance in there. So you use DPC when the device doesn't support poison, but if it does support poison, DPC is still nice because it turns a whole bunch of other PCIe uncorrected errors into effectively a corrected error. So it is useful for reducing the blast radius generally. Do you see what I'm saying?
No, I'm not quite sure what you mean by it translates into corrected errors.
Well, it's they don't cause crashes. So if you look at the PCIe spec and read about what DPC is for, it allows you to survive fatal errors without making them system fatal. It becomes fatal to the link and the link goes down. And so that's nice because I can have other like DPC. Well, if DPC by default does not trigger for poison, you have to promote poison to fatal, and then DPC will trigger DPC. Sorry, poison then will trigger DPC. But DPC can be triggered by a lot of other PCIe errors, and they're ugly errors. The link is unhealthy, and so you can shoot the link, and then clean up the software mess, reconnect the driver, and bring the link back up. And the process of retraining the link may fix the problem, or maybe sending perf to the PCI device will reset it enough that something clears up, or it won't come back up. But at least at that point, the rest of the system's running for an otherwise fatal PCIe error. Do you follow what I'm saying?
Yeah, I don't know enough details of the PCIe to, yeah, but I hear what you say.
Yeah. So imagine a situation where I have 16 GPUs on one host, and I've got them divided up between customers and virtual machines. I don't want to take all the customers out when one of the GPU fails or when one of the GPU PCIe links unhealthy. So anything I can do to reduce the blast radius and just hurt the customer that had the hardware failure and not all the other innocent bystanders is a good thing. So yeah, we can
One,
dig in.
one, sorry, one question on this
Go
stream.
ahead. Yeah, go ahead.
Yeah, I just wanted to know, like, I understand that enabling the DPC on the furthest downstream port, would there be a case that, hey, we want to actually have DPC enabled on the switch upstream port? Yeah, or on this, like, maybe we want to keep the switch alive, right?
Yeah, generally you want to keep the switch alive. Maybe if there's I guess like if there's a fatal error in the switch,
Mhm.
so the fatal error cases, it may be appropriate to have DPC set up everywhere. For poison, we want it as downstream as far as possible. But I don't understand the fatal ones well enough. Like we might want to ping Anil, or if we can get Erwin Saar from NVIDIA to consult with us. But like we could dig into that with PCI experts. I'm not 100%
What
sure.
question again, sorry?
Um,
Yeah, go ahead.
so the question is, okay, let's exclude poison. There are other fatal PCIe errors that DPC is nice for recovering from. And the question is, would we ever want to do that on link 2 because there could be something unhealthy about this link. And so DPC might still be useful here, but I'm arguing not for poison. For poison, we'd promote the poison on the downstream link, but I don't know if
Oh,
DPC would still be
Usually it's
useful on
kind
the
of
upstream link.
risky to turn it on.
I think I heard you say upstream port. It's not.
Upstream link.
Okay.
Link 2 is the upstream link, and link 3 and 4 are the downstream link.
On the upstream link, it's not going to be on the okay. So on that link, DPC can be triggered, but it will be on the downstream port.
Oh yeah, absolutely. But that's not the question. The question is,
An entire hierarchy below that, because I think what Suke was saying, we want to keep the switch alive. Switch will not be alive if you kill the link too.
understood. The question, that wasn't quite the question. The question was, so we know that we want to do DPC downstream as far as possible, but are there errors where DPC is still useful? Because if I have 2 switches and I take one switch out, that sucks, but it's better than taking out the whole machine. And so if I have a fatal error on this link, DPC might still help. And go ahead, Nita.
The problem with that is, yeah, you're right. If you have a fatal error due to the switch, that might help. But sometimes the fatal errors that travel all the way up to the, and get detected at the root port are due to an PCI Express endpoint 2 or 1. And so that is going to also take down everything under, that root port, even though the fatal error was kind of, quote unquote, the fault of, endpoint 2 or 1. It's just that it got detected at the root port.
Yeah, so anything beneath that downstream port is isolated. It doesn't differentiate that there is a split down the lane.
Yeah, we're all aware of that because it takes the link down. So
let me allow me to ask Suke's question again, because I think I'm not really hearing that question still.
Yeah. So basically, like, we understand we want to limit the blast radius, right, by keeping it as downstream as possible. I was just wondering, are there cases where, hey, yeah, even though we take everything down along with the switch, if we have, the switch going down, are there cases where it makes sense to have it enabled so that, yes, you reset the everything downstream from the switch as well?
yeah.
Everything downstream for the switch. So let's clarify further. So you have problems somewhere beneath the switch. It could be PCI link 3 or 4 and point 2 or 3 respectively. Okay. What you are asking is, what are you asking? Can you?
No, I'm not even saying we have problems downstream, like PCI endpoint 2 or 3 in this case. I'm saying at the switch level itself, right?
Mm-hmm. There is some problem. Something is causing uncorrected errors in the switch, let's say. Okay.
Well, like actually, let's be really specific. So if I go look at the PCIe error list, there are fatal errors, right? So just as an example, there is a flow control protocol error. It's optional, but it's fatal. Okay.
So
If I have a flow control protocol error on link 2, that may be isolated because something may have happened on that link. And so that the DPC may still be useful for that flow control error.
yeah, I think I was just still at the hierarchy that Suke was trying to explain. I understand that, yeah, for that kind of uncorrectable error also, DPC will absolutely be useful. Totally agreeing with you.
And malformed PLP is another one. That's one I should have come up with sooner.
Let
But
Suke.
that's the thing with the malformed TLP. Usually it's coming, like in the case where it's coming from a endpoint like PCI endpoint 2 or 1, it's going to get detected at the root port. And then if you have DPC enabled at the root port, you take down the whole hierarchy. So
Right.
unfortunately, there's no granularity such that we can catch errors which are due to the switch and then take down the hierarchy versus any error that just happened to travel, just happened to be detected at the root port, but was due to an endpoint.
In other words, Mita, completely agreeing. In other words, okay, whichever downstream port first detects the error, it trigger TPC if enabled, and everything in the hierarchy underneath that downstream port is affected. Okay.
Yeah.
Right.
So what you're saying is actually quite interesting, but not available.
Well, no. Wait. So if another fatal error is a uncorrectable internal error. That's an optional error, but that could easily occur in the switch. And so if I had an uncorrectable internal error on link 2, then DPC would bring the switch down and reinitialize the switch. And so that's a clear example of where a fatal error could be recovered from using DPC on an upper link. And Mita,
Exactly.
I'm not disputing your point, Mita, but I'm just the malformed TLP, some of them may be endpoint, but some of them may be appropriate for bring link down.
I
Yes.
agree with that. Yeah, I agree that some of them.
Yes, you assume that
Okay.
error has not made it to the downstream port above the switch. So yes, if switch has capability to handle the error internally and not propagate it to the downstream port above it in the hierarchy, then yes, the port above it will not trigger DPC. That's true.
Okay, so I guess there may be some cases where I guess enabling DPC on the root port of the switch, the upstream port of the switch could make sense.
Yeah.
I'm just speculating here, so yeah.
Yeah, I think so. And I think that's something we could stand to dig into a little bit more, but I think there are some errors that it would be useful. But not all errors,
Yeah. Thanks for the clarification, guys.
Yeah. Okay. So I'm gonna go to a fun case. This is a very interesting case because you can have some GPUs transfer data to one another. And when you do that, the CPU says, hey, you use this memory range GPU, and hey, GPU2, you use this memory range, and talk to each other. And then the CPU goes away. And ideally they do PCI to PCI transactions, but sometimes they're just situations where you end up going through memory. And this is real world, I've seen it. And
it's peer-to-peer through DDR, right? That's,
yeah, exactly. Peer-to-peer through DDR. And so you're not going to get any machine checks because the host CPU is not touching things. And, so the host CPU isn't consuming anything. And the consumption is, let's say GPU1 writes to memory. Memory is bad and corrupts the data, poisons it, and sends it to GPU2. If you don't pay attention to that, you can have endless corruption going on and not know it. So, this is an example of why you need to pay attention to PCIe.
And that would be silent data corruption, right?
Yeah. Oh, yeah. And this GPU might happily use that corrupted data, and it might do it for a long time. And it may be hard to notice, especially if the corruption's not real blatant. Sometimes uncorrected memory error is sparse and affects handfuls of bits. And so, yeah, it may be a while before you figure out, this thing that I'm doing is looking kind of wrong. Okay, so and then another consideration is that you sometimes, we call them in the GPU spec, they call them X links, but it's just like MB link or whatever. Some folks use kind of networking stuff, but there's often some sort of peer-to-peer transaction that doesn't go through the host at all between GPUs. And so that's really interesting because you could have the GPU on the right poisoning something, and the GPU on the left receives it, or even worse, you could have the host poisoning something, and somehow, it winds up in another host's memory. And so this is kind of another reason I'm thinking RAS API, GPU clusters. We want to see when things are creating poison, and we'll know how they're clustered. And we want to be able to see that, so a GPU passed poison. And it may be that we need GPU vendors to help us lock things down when, when there's something funny. So anyway, this is a scenario that keeps me up at night sometimes. And then there's upstream poison, which I've already been talking about indirectly, but you have HBM, or something, or maybe it could be a cache in the device, to be fair to the memory vendors, and it poisons stuff and sends it up to the root port. And like I said, this is the key problem I have is I don't know how to tell that a device is generating poison, and so we want the RAS API to help us solve this problem. And there's also no standard way to clear poison in PCIe devices. Usually you have to send it a burst or reset it, and that'll do the trick. But if you think a PCI device is generating poison, then pay super close attention, beware. Because it may be a while before you figure out who's at fault. And then clearing poison is fine because it's clear when you reinitialize memory. So the system reboots, and usually firmware will trigger a memory test of some sort. And even if you skip memory tests on an ECC system, you need to make one pass through memory because you need to write the correct ECC into memory so that you don't get a bunch of ECC errors. And so the firmware will put the memory controller in a mode that allows it to somehow set the ECC to the correct value for memory, and then it'll go put the memory controller in normal mode so that it detects uncorrected errors again. And it's tricky to clear poison at runtime because you don't really know what part of the cache line is corrupted. So you know that a cache line is corrupted, but you don't know where in the cache line. So if you do a write to the cache line, you say, well, I'm going to write, a byte at a time and clear the cache line. That should clear the poison. The memory controller and the memory can't keep track of what's been written since the memory was poisoned. They don't know. And so, but if you write all of it at once, it can go, oh, you just sent me 64 bytes. I will put that in memory and set the ECC to the correct value. But if you do anything less than the cache line granularity, then what happens is you do a read, modify, write. And so you read poison, that's consumption. And then when you're writing it back isn't going to fix that because you're not clearing everything in the cache line. And even if you do clear it, there's no guarantee that the memory is working. So, you might still have future errors. And some CPUs, are looking, there are ways to clear poison. It could be a special opcode. Sometimes you can use a multimedia instruction that has a monstrously wide register just to do a cache line sized write all in one atomic access, and that'll do the trick. But it's kind of hit or miss. It's not standard by any means.
And by the way, Drew, it's getting more and more complicated because there are features now that are becoming more and more prevalent in the server space, like MTE, for example, memory tagging. So you add tags to the data and they need to be protected, but often the tags are they are small compared to the data. So architecturally, you can aggregate them in memory. So suddenly, if you have errors on your tag, then it's something that is a problem, I think, also for poison and poison clearing.
That's a really good point, Seb. I hadn't considered that. Yeah, you're absolutely right. Yeah, that might be something we want to talk about and say, it may be that what we need is different processor architectures to, we can just give each processor architecture a request to, come up with a safe way to clear things out for the OS, because the OS, when it receives poison, it doesn't know who caused the poison, but it's generally pretty sure that address is poison because it just fetched an address and it got poisoned. So it needs to stay out of it. It's like if you see dog droppings, on the sidewalk and you step in it, you're not gonna be like, oh, let's step in it again. You're gonna be like, stay away from that. And so the OS is that way about it. It's like a dog dropping. Let's get away from it. But if we later with the RAS API, we come up with a way to identify that no, this particular poison page was caused by PCIe, then we could tell the OS, hey, this page is safe, you can clear it and use it again. But we'd have to come up with semantics with each CPU vendor that would survive whatever tagging or support, or maybe you have to blow the tags away and just say, this all you can do with a poison page is take it from poison to completely unallocated and fresh. But I don't know if tagging works that way. So I don't know. This is worth discussing, Seb. I don't know the answer. Another thing that is ugly is CXL memory that's shared between hosts, especially if you have like sometimes you might have a region of memory that you might share. So when I was at HP, we were working on something called the machine, which was a giant non-coherent memory parallel processing machine that would use Gen Z to connect very, very large numbers of nodes with even more memory. And that was one of the key corner cases we ended up needing to figure out was, okay, if I'm sharing memory between two hosts and it's independently initialized, then how do you clean up the mess when you get poison? You kind of need both hosts to acknowledge, hey, it's time to clean up. Or because you can't clear the poison. If I have, let's say host A and host B using a poisoned chunk of memory, if host A clears that memory, that poison, then host B might come and read it later and think, oh, I got my data. And no, host A had just blown it away. And so there has to be some handshake between them that it is safe to clear the memory. And I'm not sure how far we've gotten with that kind of clearing. I think today you just leave poison in it. And if you ever reboot the CXL memory tray, it'll reinitialize the memory. And if the memory is working correctly, it'll clear the poison. So it might really suck if you had a PCIe device that was pumping poison into the system that was somehow winding up in the CXL.mem region that was shared. So, there's work to be done there. And then when there's address and metadata corruption, you don't know the scope of the damage. So, if you lose a packet header, if you have a corrupted address, if you do a snoop and you don't get a response to the snoop or you have a transaction level timeout, then you don't know the scope of the damage. All you know is something's not working right. And so cache coherence, like you can be pretty sure that the ordering assumptions that create a cache coherent system have been violated. And that violation means that you don't know the state of memory anymore. And in some cases, it may even deadlock the system because there are expectations for the ways credits are used and released, and so someone may be holding onto a credit that causes a chain of held credits and clogs the system up. So in this case, we need to crash. The system's in an unknown state, and we need to contain the corruption. We can't really use poison because we don't know. Poison, what you do is you check the ECC or you check a parity or something, and you say, I know the scope of the damage. I am responding to the requester with poison. But here, you don't even know the requester. If you've lost a snoop, you may know that I dropped a snoop, but I don't know where to send it. Or if you get a corrupted header, who was it intended for? It was corrupted. So you really need a transaction speed response to contain the to contain the corruption, and that's where things like viral and sync flood come in. And the way viral works is when a block goes viral. When I say block, I mean like an IP, like a memory controller or a core, a mesh stop, or a PCIe root port, some sort of chunk of silicon functionality that sends coherent packets. And when one of those blocks goes viral, what happens is it enters a viral mode where all of the traffic in and out of it are viral. And it makes all of its neighbors go viral extremely quickly. And when the I/O blocks go viral, they shut off. They close traffic off and contain the error. And this such viral is typically cleared by resetting the system. Now, at HP, when I was working on Superdomes, we had something called plunging the system, and we had a super brilliant, designed with a silicon implementer crawl out, where we would crawl out and rediscover the system and figure out what was broken, and then assemble the pieces back together, plunge the fabric, clear the viral out, and we would have chopped off all of the things that were broken. So we could be missing cores or random chunks of silicon. And then what we do is hand off to the OS. The OS would take a crash dump, and we would get a hardware error log and an OS crash dump, all for the viral error. But the deal was that didn't happen that often, and it was brutally hard. It was extremely sophisticated software and somewhat error prone. And so I'm not arguing we need to go back to that by any stretch. It may just be that we do a crash dump. That's kind of what we do today is you go viral or sync flood, something gathers hardware error data outside the system, and then we reset the system, and we don't get much OS data. And it's not perfect, but it's generally pretty workable. And when that doesn't work, then we start debugging. And when we debug, then that's kind of where we wish we had what software was doing. But the problem is that back in the old day when I was doing that in HP, we would take the crash dump and then build this thing called a tombstone, and our customers would just email us the tombstone, and we could attach a debugger and see exactly what processes we're doing, and we could see the data, and we could see the hardware state. But that was before there were a lot of security concerns and privacy concerns. And in today's world, what we may need to do is come up with a way to generate a hardware crash dump with a unique identifier that also the software sees. And if we can somehow get a system to maybe warm reset and then try to gather some data in software, then maybe we could have an identifier that we could use to correlate the hardware crash dump with the OS's crash dump. But that's maybe the best we can do today. And finally, poison is important for containing corrupt data. Poison generation tells you what you need to fix. Poison consumption is how you keep corruption from spreading. Don't assume that memory is at fault. I'm looking at Evan as I say that. And use DPC when you have devices that don't support poison. And that's it. So I hope that was interesting. I'll put this where people can take a look at it later in the work in progress folder, if you are in the presentation folder. And I welcome feedback on the paper as well.
Yeah, sounds great.
Thanks.
Thanks, Drew.
Thanks, Drew. That was very informative. Thank you.
Cool. Well, I hope it helped, and I would love your questions. And Seb, you in particular, you gave me some things to think about today. So thank you. Okay. So I think that's it. It's pretty late today. We got 4 minutes, so maybe we call it early. Feel free to ping me during the global summit, and I would love to meet all of you. I mean, anyone that's there, please reach out because it'd be wonderful to meet in person. And I'll reward you. I'll have a pile of these to give out. So if you want one of these, let me know.
Looking forward to it.
Me
Same
too.
Hey,
as
please, Drew, if you meet somebody from Ampere there, give them one of those stickers for me, please.
Absolutely. Do you think Harv
Uh,
will be there or someone?
I don't know who is going to be there. I need to reach out. I know I'm not going to be, unfortunately.
Okay.
But
Are you
we'll
in
see.
the Bay Area?
No, in Portland. Remember,
Okay.
yeah.
Okay. Well, you know what? Yeah, I'll try to find someone from Ampere. And if you send me your address, I don't mind mailing you one. So,
Don't worry, but it's just
I mean, it's just an envelope. It's no big deal.
yeah,
But let
but
me know.
it's cool. Little sticker.
Okay.
Good idea.
Cool. Well, I just want to have some fun.
Yep.
Well, it's important to build a sense of community. I think the better aligned we are, the more we have a sense of community, the more alignment we're going to get, and the more we're going to make it easy for each other to get what we want. Because at the end of the day, we
Yeah.
all want our stuff to work.
Yep, that's true.
Awesome. Okay.
Thank you.
Hey, thank you,
Thanks.
everybody. Talk to
Thank
y'all later.
you.
Bye.
Bye.
Bye.